Hi folks. Chapter 2 is all about interpreting data and figuring out if a set of data that we're looking at can be modeled by some of the functions that we know. So today the goal is to review linear functions, quadratic functions, and exponentials so that when we get to that data set interpretation, we know what those things look like. Okay, so make sure you have a calculator ready and a note card, a blank note card. First step is just linear functions. The most basic form is y equals mx plus b, and m is our slope there, and the b is the y-intercept. So to start out with here, we have a table of x and y values, and we're supposed to explain why it's a linear equation, and then find that equation in that form we just talked about. So here, if you notice, the x values are increasing by 1 each time, and then if we look at the y values, what makes a function linear is seeing that the y value jumps by the same amount each time, or a constant amount. So each time, if we look at our y values, it looks like we're subtracting 3 all the way through the table. Okay, it has to be consistent, but that constant jump is actually our slope. So that tells you m is -3 here. Okay, that's only going to work for us if our x values are counting by 1. Otherwise, we can use the formula y2 minus y1 over x2 minus x1 to figure out that slope as well. Okay, to show you what that looks like, if I just choose on these 2 points here, okay, y2 minus y1 would look like 3 minus 6, and then on the top it would look like 1 minus 0, so that's a -3 over a +1. Okay, so 2 ways to do that. The y-intercept is an ordered pair, and it always looks like 0, some number. Okay, in our table we're just going to go look for 0, and that'll get it for us. We've got 0 with a 6 here, so that indicates our b is 6. So why is it linear? It's linear because our y values are decreasing by 3 every time. And our equation is y equals -3x plus 6. Now, I want to take the time to talk about other forms of a line, okay, because you will need them for when it comes to your homework. So if you're given a table, or instead of a table you're only given 2 points and you want to find the equation, okay, you'll have to use this slope formula that I just talked about, but you can also use point slope form. Okay, it's called point slope form because the slope is here and the ordered pair that you're given is right there. Okay, so that's one form. The other form of a line that you need to know is standard form, and this is probably the one you're the least familiar with, but that looks like ax plus by equals c. So there's a couple rules about this. First of all, the x and the y are on the same side of the equal sign, but also a has to be positive, and a, b, and c have to be integers. Okay, so that means no fractions or decimals are allowed here. Okay, so if we wanted to change our line to standard form, our first job would just to be get that 3x over to that side, and we can add it over. 3x plus 1y equals 6. And then we're actually good here because our a is positive, and all of those are integers. Okay, so that would look like standard form for when you go do problems on your homework. Next up, we're going to review quadratic functions. Okay, so these are a little bit more interesting. Okay, we've got here the general form. We've got to have a squared term. That's why it said a can't be 0 here. Otherwise, it's not a quadratic function. It would be linear if that part was missing. But then these letters kind of tell us something else as well. Our c is our y-intercept, And A will tell us whether we're opening up or opening down with our parabola. Positive would open up, and a negative would open down. Okay, so we're going to go ahead and talk about these things right here. So here's our function we're working with, 2x squared minus 3x minus 2. Direction of opening we decided is by A, and positive means it opens up. And then we want to find the x-intercepts. There's two ways to do this. Okay, we can do it by hand algebraically, and we can use our calculator to help us as well. So sometimes I'm going to go ahead and ask you to solve algebraically or find the x-intercepts exactly. So let's do that for this one here. In general, when we're solving a quadratic, there are three ways to do it. You can solve by factoring, if you can. Then you can solve by either completing the square or quadratic formula if factoring doesn't work. Okay, both of those methods work on every single problem, but there's better times to use each one of them. So looking at this equation, I'm going to try to factor first. We want to always look if there's a greatest common factor that can come out at GCF. In this case, there can't. So this would be what you learned as frowny face factoring last year. Okay, but I'm going to show you a little bit of a shortcut here. Still the same first step. 2 times negative 2 gives us negative 4. And we're still looking at the factors of negative 4 that could add to negative 3. This is going to tell us if it's even possible to factor. So for us, we can factor this thing with a negative 4 and a positive 1 to get that negative 3. And here's where you would go to frowny face factoring, but here's where I'm going to have you change the instructions. This would be super easy to factor by saying x times x if this number 2 wasn't here. So if we want to eliminate that number 2, essentially we can divide by 2 on all these pieces, and then it becomes easy factoring. Now that does create some fractions here, but we don't actually have to worry about it because we use these numbers. All we're going to do is divide those numbers by 2 and see what happens. Okay? So the negative 4 divided by 2 gives me a negative 2. That'll go in my first slot. And then this one right here we'll call plus 1/2. Now the only issue with this here is when we're generally factoring, we don't like to have this plus 1/2. Okay, so to eliminate this, we can call it 2x plus 1 instead by multiplying by 2 to eliminate that fraction. And then our x-intercepts are just where those equal 0. So the first one would be 2, 0. And the second one, when we solve this one, would look like a negative 1/2, 0. Because we're just trying to solve, it's really okay to leave it in this form because we're just switching the sign of that. Factored form would have to look like this, but our goal was to solve. The vertex can also be found algebraically, and in fact, the vertex is always a rational number because by definition, it's the opposite of b over 2a. So it looks like a fraction right there. Our calculator may not always recognize it as a fraction, so you have to be careful on that. It's always a nice rational number. So here the opposite of b looks like positive 3, and then 2 times a would look like 2 times 4 or 3/4. Okay, so there's my x value. And then we'll go ahead and type in this to get the y value. So 2 times 3/4 squared, and then minus 3 times 3/4, and then minus 2. Okay, I'm going to go ahead and change that to a fraction because I started with a fraction, but fractions or decimals in general are fine with me. So that's a negative 25 over 8 for my vertex. Okay, now we're going to go to the graph and talk about how all this looks, and I'll show you how to get these same numbers from your calculator. Okay, so first thing we're going to do is go to our y equals, clear out anything that's there. You want to check out up above because last chapter we were dealing with our stat plots. If any of those are highlighted, what you can do is just go up and hit enter to get rid of them. Okay, so I just turned mine on, hit enter, that'll turn it off. Okay, another option, remember if you go to second y equals, you can turn them off through there as well. But we're going to type in our equation, 2x squared minus 3x minus 2. And then to get back to a regular 10 by 10, we'll hit zoom and then 6 and see if we need to adjust from there. Our whole goal is to make sure that our graph is kind of in the middle of our picture over here, and also so that we can see everything that we need to put on there in terms of critical points. So we're looking for x-intercepts, y-intercepts, max and min. Now it looks like I can see all of those from here, but I've got a lot of extra wasted space. So I'm going to go ahead and cut this down to a 5 by 5 instead of a 10 by 10. So click on Window, and we'll adjust all those numbers to 5s instead. So -5, +5, -5, +5. Okay. And that's a more clear view of our graph now. Okay, so let's go ahead and put on that x and y axis. Okay, if you don't have a straight edge, pause the video so you can grab one real quick. Okay, we're just going to go through the middle since we didn't adjust our symmetry here. It's pretty close to the middle, so that's not too bad. But we did change this to 5. Same thing with our y-axis. Now, I already know my values to be able to graph this. Okay, they're on there, except for the y-intercept, which we'll talk about. But what I want to do is show you how to use your calculator to do this. Going back to our ordered pairs, for the x-intercept, the y was 0. So the easiest way to find y-intercepts, or x-intercepts actually, is to take in your y equals and put a second line at 0. That allows us to trace the intersection of the curved and that horizontal line instead of having to trace the x-intercepts. It's a little bit faster, and I'll show you what I mean. So go back to the graph. And what we'll do here is hit second and then trace, because that gives us some options to calculate stuff. Okay, so second, trace, and then this is where I was talking about you've traced the 0 before to get the x-intercept, but I'm going to use the intersect button instead. Okay, so go down to 5 for me. And then the prompts are going to say first curve, second curve, and then guess. Because we only have 2 curves on here, you can just hit enter, 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 and it'll give you whatever intersection you're closest to. Okay, so this one was at -1/2. That's on our graph. Okay, so let's go ahead and plot that point. In general, you want to label it as you go, so watch out where your curve would be, and then here we can label that to the side. Okay, I say in general because sometimes I don't have you find this stuff first, and you don't want to forget anything that you write down. The next one looks right at 2. Anytime something looks nice, you can just guess by hitting trace. And then if you think it's 2, hit 2, enter, and if it pops up as 0, you guess correctly. So anytime they look rational, you can guess. But again, I'm going to show you with your calculator. You hit second, trace, intersect again. And this time, if your cursor was over here, you just need to move it so it's closer to this side using your arrows. Once it's closer to that one, you hit enter, enter, enter 3 times again. And there's the 2, 0. Again, let's label that. Okay, our minimum. I'm going to show you how this works on the calculator. You want to hit second, calculate again. And then we're going down to the third option, minimum. Now, the prompts for this one will say left bound, right bound, and then guess. So we have to be on the left side of that vertex, the right side of that vertex, and then we can hit enter. You can use your arrows to do this, or you can type in x values. So I know it's between 0 and 2 somewhere. I can actually type 0 in and then hit enter, and then do the same thing over here. I can type 2 and then enter to make those cursors move a little bit faster. Okay, those are my numbers, and I'm really glad it popped up this way. I told you that the vertex is always rational, but your calculator doesn't necessarily know that. This has 0.75 and then a bunch of zeros and random numbers on the end. Sometimes your calculator will show up with some error. It'll either have a lot of zeros on the end of your number or a bunch of 9s. Okay, your job, if that thing is a vertex, is to know that that's actually a rational number and that your calculator is just messing up a little bit. Okay, so you have to write it as the 0.75 exactly and the -3.125. Okay, that or the fraction that you got originally was fine. Okay, we want to graph that. About 0.75 is here. Negative 1, 2, 3 and a quarter here, a little under a quarter. Okay. And then from there, I'm going to go ahead and label this one as the decimal, just to show you either's fine as long as you make sure that you're writing all those decimal places. If something repeats, you can use the bar to signify that. Last thing we want to do is just go ahead and connect our curve. Looks like we're missing one place when I try to connect these. It crosses over the y-axis here, so we have a y-intercept. Remember from your equation, it's just whatever your constant is. So ours is at -2. If you want to see that on your graph, a y-intercept is always, remember, 0, y. So you can plug in x equals 0 by using trace 0 to see that as well. Okay, so plotting that and labeling is our last step to finish our nice curve. Okay, do the best you can connecting these. And there's your comprehensive graph. Remember on these we don't want any arrows, and we want to make sure everything is labeled nicely, dimensions on the outside. Next thing we're going to do with quadratics is Newton's law. It's a very common application of using a parabola here. So what I want you to do, we're going to make a note card for this, but we're not going to put all the extra stuff, just what we need to know. So I want you to label your note card Newton's law, but then I just want you to write this formula here as you see it. And then if you need it, writing the pieces that we don't know. Okay, you know h stands for height, you know t stands for time, okay, but if you need it, write initial velocity is v naught, that 0 is said v naught, and then the initial height is h naught. The last little variable we've got here is g, and this is actually a constant for every single problem. Okay, on the surface of Earth, the g, the initial, the acceleration due to gravity here is always the same when dealing with feet or meters. So it's 32 feet per second squared if we're talking about feet, and it's always 9.8 meters per second squared when we're talking about seconds. Okay. So pause the video and jot that down. I do want that gravity on there in that formula, and then you decide if you need the v naught and the h naught of what those things mean. Okay, from here what we're going to do is write the relation between height and time after this ball is released. Okay, that just means write the formula that is given here with our numbers plugged in. Okay, so in the information here it says a ball is thrown upward from a height of 15 meters with initial velocity of 20 meters per second. Both of them are dealing with meters, so what we're going to do is take half of that real quick using our acceleration due to gravity that works for us. So meters with 9.8, half of 9.8 is 4.9. So I'm going to write h of t equals, we've got a negative 4.9, and then t squared comes next. That's our variable like x, it'll stay in every problem. Okay, next up we're going to add the initial velocity. We were told that was 20 here. Again, we'll tack on t. And finally, we start with our initial height, so plus 15. It is possible that you would have a situation where the initial height was nothing, so it started from the ground, or the initial velocity was nothing. It said instead of being pushed off or forced object, it would just be falling. So if you ever see an object is just falling, it would not have an initial velocity. So this piece would be missing here in the middle. But now that we have our equation, we can answer some questions about it. It says, how high is the ball after 3 seconds? And then when does the ball hit the ground? Okay, so how high is asking for what is the height, and it gives you the t in time here. So really we can just plug in t equals 3. But in general, on your homework, you're going to have a lot of problems dealing with this same equation. So a lot of times it is nice to spend the time to actually graph it. Okay, so let's go ahead and in our y equals, type in this equation. So clear out what we've got here. Negative 4.9, and then x squared then plus 20t, so 20x, and then plus 15. Again, I'm going to start with a Zoom 6 window and see what I need to do to adjust it. All these parabolas open down because we're talking about a ball traveling. Okay, it doesn't go up forever, it goes down until it hits the ground. So, in general, we can answer the questions without seeing the whole graph if we don't need to see the whole graph. What I mean by that is B and C here are only talking about 3 seconds, and I can see where 3 is on the x-axis, and it's talking about the ground, and I can see the ground in the picture. Okay, but if you have to adjust this to see the entire thing, you can use 2 things to help you. The first is, I know that my y-intercept is 15, so I have to go up at least 15, usually more than that. Because usually if you're talking about your graph, your y-intercept is here, but your maximum is higher than that even. Okay? Another thing that's more useful is the vertex itself. That'll tell you the highest value on your graphs to be more specific with it. Okay? So remember that's the opposite of b over 2a. So for us, that would be the opposite of 20 over 2 times a gets us back to the 9.8. And that would be the value of our vertex. Okay? So once you get that, you can literally trace it. So I'm just going to type it in as is instead of simplifying it. Okay, so 20 over 9.8. If you trace it, there's the y value of your vertex instead of plugging it in by hand since we had the graph ready. That tells me my maximum's 36 at least. So if I go to my window and my y-max, I'm going to just change this to 40 and count by 5. And then that would allow me to see the entirety of my graph so I can answer all types of questions. For this one, we just have to type in t equals 3 or trace 3. And it gives us 30.9. That's talking about the height. It's measured in meters here. Now technically this acceleration due to gravity is approximate, so all of these are approximate, but it's okay with me if you see exact and write exact, okay, because there are going to be some that we do really have to round in these situations as well. When does it hit the ground? Okay, again, our y equals is already at 0, but that's what the height of the ground is. So we're just going to trace the intersection like we did on the last graph. So hit second, trace, intersect. And then just make sure your cursor is closer to this one because we don't want the negative value. We can't have negative time, so we only want this one on the right. As long as your cursor is on the right of the vertex, it'll work to hit enter 3 times. This is an irrational 0 here. Okay, it's really ugly looking, no repeating, it doesn't terminate. So we're just going to say approximately, and then it doesn't give us any guidance on rounding, so 1 decimal is great for me. So 4.7 seconds. And that's it for Newton's law. We're going to switch track to talk about exponentials. These are probably the one graph out of the 3 that you're the least familiar with, okay, but you have seen them before. The general form looks like y equals ab to the x, where a is the initial value, okay, that's what this tells you right here, initial being the y-intercept, okay, so 0 something. When you plug in 0, this always cancels out to 1. Remember, anything to the 0 power is 1, so it's just left with the a. So this right here is our y-intercept for this graph, which we always call the initial value. Then b is your base, or the rate that you're growing or decaying at. Okay, so linear functions had a constant jump that we were increasing or decreasing by. Exponential functions have a constant rate that you're multiplying or dividing by. Okay, it does say a can't be 0 again because that would make all of this 0. That's a constant. B has to be greater than 0 again because if we have a 0, everything goes away. But also if we have a negative, what that does is kind of alternates over the x-axis, kind of like that, so it doesn't work for us either. And then b can't be 1 because 1 to anything is 1, so this is a constant at y equals a again. Okay, so those are kind of the rules, but the a tells us about reflection, whether we're going up from there or down. We won't have that very often, b smaller than 0, especially in context, so you don't have to worry about that very much. What you do want to think about is the base. The base, or the rate, will tell us whether the thing is growing or getting smaller from left to right. Greater than 1 is growing, because when we multiply by a number larger than 1, it gets bigger. And then between 0 and 1 is going to take care of getting smaller. When we multiply by a fraction like 1/2, the number gets smaller every time. And again, we're not going to ever have negative in that situation. Essentially what the graph of growth looks like, it gets larger. This point, our y-intercept, remember, is 0 and whatever a is. And then we also have a horizontal asymptote at 0 here. Because of those restrictions on the a and b, we can't ever be below the x-axis without a translation of some sort. Decay has a lot of similar features here. It's just going to get smaller from left to right. We still go through 0a. And we still have a horizontal asymptote of y equals 0. With those features being the same, our domain and range for both growth and decay are the same. Left to right, all real numbers work for us. And bottom to top, the lowest value on both of these graphs is 0. So it's going 0 to infinity. Okay, remember, we're not including it here because there is an asymptote. Now that we know what the graph looks like, we're going to talk about how we know in context that something is exponential. So our first example here, it says the towns of Scarsdale and Ampleton both have approximately 8,500 residents. And then over the next few years, the population of Ampleton is expected to increase by 2.3% per year, while the population of Scarsdale is expected to decrease by 0.9% each year. Anytime you see a rate in a percent, that tells you it's exponential. Okay, so that's a constant multiplying factor, always exponential. So remember, the general form for the equation is y equals ab to the x, and our job is to fill in what we know. Our initial value is a, okay, that's whatever we start with, and our rate is b. Okay, but we have to think about increasing and decreasing as well. So when we look at Ampleton, we're going to go ahead and start with y equals, and our beginning value for both these towns was 8,500. So a is 8,500, but Ampleton was supposed to increase. Now if I change this to a decimal, that tells me r equals 0.023. But remember, in order to increase, the base has to be greater than 1. That's because when we're talking about a rate or a multiplier, we want to make sure when we're dealing with percents that we take into consideration what we started with. We started with 100% of those residents, so we want to say we increase it by the 2.3 and get 102%. So that would look like 1.023 when we add the 100%. So when you see these words increase by or decrease by, you take 1 plus or minus whatever your rate is, okay, every time with the increase by or decrease by. Then we can just put to the x. Over here, Scarsdale will be very similar, 8,500 still, but this time it's decreasing by 0.9%. So our rate, if we move this over 2 places, looks like 0.009. Okay, but again, we have to go ahead and subtract that from 1 since we're actually decreasing. Okay, now do be careful, this is 0.9%. So really, if we're thinking about 100% minus 0.9, okay, that's 99.1%. So that'd look like 0.991 when we move it over. Okay, calculator's your friend if you're stuck on that. We are going to use our calculator in the next one. It says compare the projected populations after 5 years. Okay, so here was our initial value. 5 years later just means we plug in 5 for our equation above. So let me get out of my graph here and just type that thing in. 8,500, 1.023, and I'm raising it to the 5th power. When we're talking about, I'm going to say ampleton here, when we're talking about population, we have to make sure that we're rounding to an appropriate value. So here this is 9524 because we want a whole number for people. Make sure your number is reasonable. It was supposed to increase, so it has to be larger than 8,500. Over here, Scarsdale. Type it in the same equation, but our base is different here. It's just the 0.991. Okay, so I'm going to change that. And this is about 8,124 people. So after 5 years, let's go ahead and find out what the difference was. 9,524 minus 8,124. Ampleton had about 1,400 more people. Than Scarsdale did. Alright, and that's it. Okay, you're going to have a lot of problems very similar to using this y equals ab to the x, but you got to remember if you see increase by or decrease by, you have to use that 1 plus the rate. If you don't see that, if it says it's just this percent of whatever you had before, you can keep that rate used as your base. This does have a special name. It's called either the growth or the decay factor. I can't remember if your homework asked questions like that, so just in case it does, that does have a name of that term. Last thing we're going to do with exponentials is talk about their graphs. It says find an equation for the exponential function at the right. Okay, so we're given 2 points, and just like with a line, we can draw an exponential through 2 points on a graph, as long as it's not a vertical line. And all we're going to do is go ahead and start out by writing these as an ordered pair, both of them. And I always recommend that you write the bigger one on top. Okay, and I'll talk about why here in a second. What we're going to do is actually write a system of exponential functions to actually solve for the missing pieces that we need. If we think about the equation of an exponential, the two missing pieces that I'm talking about are the a and b values. So what we're going to do is plug in what we know. I know x and y, so I can write an equation with x and y plugged in for the first one. So that would look like 405 equals ab to the 4th power for the first one. I'll do the same thing for the second one, again just plugging in x and y. So that looks like 15 equals ab to the 1st power. This is a system of equations because I've got two equations that are going to allow me to solve for one of the variables. Now, what we're going to do to solve here is think about eliminating a variable. Okay, you've solved systems before with substitution and elimination. Okay, because of how this is set up, the a value is always to the 1st power, so it's actually easiest to eliminate those. Okay, but to eliminate them, we actually have to divide these systems, because a divided by a would get rid of it instead of adding or subtracting like we did with lines. Okay, that's why I had you write this the higher number first, is because when we're dividing, we want to put that bigger number on top. Okay, so what we're going to do is divide this straight down. So first of all, we're taking the 405 divided by 15, and a lot of times this doesn't come out exactly nice, and maybe a little bit uglier than this whole number that we came up with. And then over here, a divided by a is 1. Okay, so I don't need to write that. And then b to the fourth, I'll go ahead and write this out so you can see it. B to the fourth divided by b. Remember our rule here is to subtract those when we're dividing because there are 3 more on top, so that would be b cubed. Now to get rid of that cubed, we take the cube root, but I'm going to actually write it this way to take care of those other weird powers as well. So taking the cube root is the same as raising it to the 1/3 power because our rule here is to multiply when we take power to a power, and that cancels those guys out. And then the cube root of 27 is 3, but again, it doesn't necessarily have to be rational there. Okay, whatever you get, we're going to use it. So then we can take our b and plug it back in one of these equations to solve for a, just like with substitution with linear systems. Okay, so b we're substituting in right here. So 15 equals a times 3. I just chose this one because it was smaller numbers. You can use either. And that gives me a equals 5. And now I can write my equation. Y equals a value was 5, and our b value is 3, raised to the x power. Okay, so 5 here is whatever this was. Our scale isn't clear enough to show us that. And then 3 is what we're multiplying each time as we go through there. Just to show you it works, what I'm going to do is type in the equation in the y equals. It's always good to check it if you can. And then we're just going to go to our table to see if these numbers pop up. So second graph will bring up the table. And mine's weird. Let me fix it real quick. I want to start at 1 and count by ones. So 115 is right there. If I go down, 405 is there. Okay, so it checks. All right, the last problem is yours, 1 through 6 here. I just wanted you to tell me if these are linear equations, quadratic equations, exponential, or something different based on what we just talked about. Okay, so pause the video and do those for me. All of these ones were ones we knew. Okay, so take a look at what I've got here. Make sure yours matches up. And if you have any questions, please come see me.